Chapter 6, Electrochemistry. The purpose of this video, guys, is to show you how to use the Nernst equation in order to do calculations regarding a cell potential other than the standard cell potential. So a cell potential is really just made up of, you've got two cells combined together, and they have electrodes, which are metal electrodes, and they're floating in solutions which are made up of the same metal ions of the metals themselves. This is connected to a voltmeter, and you have the salt bridge, which is allowing the circuit to be complete and electrons flow full circle. So if we look up here, we see that I have two standard reductions, one's for aluminum, one's for copper. How to determine which one of these reduces, which one oxidizes, these are both reductions, but the more positive one is always reduced. So in this example, this is going to be reduced and this is going to be oxidized. Now, with that being the case, and I'm trying to figure this out and doing the calculations with this, so I'm going to write these out into the two half reactions. Where this one is reduced, so it's staying the same, so it's going to be 0.34 volts. And the other one is going to be reversed that we actually have. So since it is being oxidized, you're going to say Al naught yielding Al ions plus 3 electrons. And this one was negative 1 point, or it's actually now going to be positive because we are flipping it. So positive 1.66. So when I combine these two together, you notice that we have 2 electrons here and we got 3 electrons here. Well, we got to make these the same, so we got to make them find the common denominator between the two. So 2 and 3 is going to be 6. So that tells me that I need to multiply the top by 3. So that's 3 here. That's going to be 6 here, and this is going to be 3. Now we won't touch this at all because a volt is actually a ratio. It's a joule per coulomb, and since it's a joule per coulomb, anything you multiply it by, it's not going to change it because it's like saying you're going to multiply the top and bottom by the same number. This bottom one right below this was 2, this is 3, so we need to multiply the bottom by 2, so this is 6. So 6 is the common denominator for the electrons. So those are going to be canceled out because they're the same on both sides. So when I write the overall equation for this, I'm going to say 3Cu 2 plus 2 aluminum metals yielding 3 copper metals and 2 aluminum ions. And then you're going to combine these two together to get the overall E naught of the cell, which is 2.00 volts. Now, when you use the Nernst equation, we're calculating this at actually different conditions other than standard. Standard conditions are 1 molar solution in each one of these solutions. It's at 25 degrees Celsius, and it's 1 atm of pressure. So you can modify these and change these up. And let's just say that instead of us having 1 molar solutions in each one of these, let's say that it's going to be a 2 molar solution of the copper ions, and it's going to be a 1 molar solution for the aluminum. Alright, so using the Nernst equation, what it is it's the E of the cell equals the E naught, which is what we calculated right over here on the right, minus your universal gas law constant, which is 8.31 joules per Kelvin mole, times your temperature in Kelvin, over the number of moles of electrons transferred, which we determined up above here was 6 moles of electrons, and then that whole thing is multiplied by Faraday's constant, or the N is multiplied by Faraday's constant. Now this is a constant, and this is 96,500 coulombs per mole of electrons. And then to this whole thing, you will also multiply this by the log of Q. And Q, just like K when you learned your equilibrium constants, is products over reactants, and it's raised to whatever the coefficients actually are. And this is only for solutions that this can take place. So if we look at this, we have a 1 molar solution of copper ions, and it is a coefficient of 2. So you would say 1 raised to a power of 2. And then over on the other side, on my reactant side, I'm going to say a solution of 2 molar, and it's a coefficient of 3, so it's raised to a power of 3. And this right here tells me what my Q is for this example. So just shrink everything down a little bit and give myself some more room. Now what I'm going to do is I'm going to solve for E, this right here. So we have E naught, which was 2.0, so you're going to say 2.0 minus R, which is 8.31, that is a constant. We're going to say that this example right here that we have is at 20 degrees Celsius instead of 25. So it has to be in Kelvin, so you're going to add 273 to it. So it's going to be 293. So you're going to say 8.31 times 293. This is going to be over the moles of electrons transferred, which we said was 6 moles of electrons transferring, times Faraday's constant, which is 96,500. And then to this, we are going to multiply this by the log of Q. And if we're looking at this one right here, so 1 raised to the power 2 is just 1. And then 2 cubed is going to be 8. So our fraction that we actually have for this is going to be 1 over 8. And now it's as simple as plugging into your calculator and solving for the answer. So after plugging into my calculator, you see that it's increased by a very, very small amount, 0.004 volts. So the overall E volts of this is going to be 2.004 volts. So very minimal change if we do change the concentration and we do change the total temperature that we have, but this at least shows you how to do a Nernst equation calculation.